Well, hopefully you've watched the video and you've timed the experiment. Let's review the setup and then we'll plug in the numbers. We've got the ring dropping onto the disc that's rotating. That's the before picture. The after picture, here it is. The sum of the external torques is 0. It's on a very low friction turntable. So therefore, we can say the angular momentum before equals the angular momentum after. And we have I1 omega 1. Well, this is I1 is a rotating disc. It's moving at an angular velocity, omega 1. We add the inertias together because they're stuck together, and we have the final angular velocity. And that's what we're going to be looking for. From the measurements that you can take with a meter stick and the masses of each object, we are able to get the inertia of the ring and the inertia of the disc. When we plug in the data for angular momentum before equals angular momentum after, this is the inertia of the disc. We have to measure this in the video. This is the combined inertia of both objects, and then we're going to measure the final. To get the angular velocity of this disc initially, I timed it for 3 rotations, but at a slow motion factor of 4. So now I have 3 rotations times 2 pi divided by 8.21 seconds was the time I measured. But you have to divide that time by 4 because we had a slow motion factor. And we get 9.184 radians per second. Now we plug that number in here for the initial angular velocity, and we can calculate a theoretical final angular velocity. And we get 6.018 radians per second. Now to get a final angular velocity experimental, I just watched it on the video, counted 2 rotations, and found the time of 8.3 seconds. Again, we have to multiply by 1/4 because that's the slow motion time. And I get 6.056 radians per second. Very close to the theoretical. We have very little error here. This I would have expected, though, to be a little bit lower than the theoretical. But then again, it could be the slow motion timing, a little bit of error there. Some kids wanted to know, how come I only measured this for 2 rotations, but that one I did for 3? Well, they worked out to be about the same amount of time. If I did 3 rotations, you can actually see on the video that this starts to slow down a little bit. There is a little bit of external torque. So I wanted to eliminate some of that, so I did it in a short amount of time. Let's check out the kinetic energy. The kinetic energy initial is just the kinetic energy of the rotating disc. We use the inertia for the disc. The initial angular velocity is measured in the video. And we have 0.395 joules. To get the final kinetic energy, I've taken the inertias, added them together. Remember, they're stuck together, times the final angular velocity squared. And I get 0.262 joules. Well, what happened to this energy? I thought we were on a very low friction bearing. There's friction in between the ring and the disc. Friction is how the momentum is transferred. And it's not external. This is all internal. So we generated 0.133 joules of waste heat in between these objects. And that makes sense considering it's an inelastic collision.